Originally, IP network numbers always fell on an octet boundary. This scheme divided the IP address space into different sized chunks or classes of addresses based on how many octets are used for the network portion and how many are used for the host number. For example, a Class C network uses the first 3 octets or 24 bits for the network portion and only 8 bits for the host portion. At this time, a central organization assigned a network number from one of these classes to businesses, governments, or other organizations based on size and need. The address class is actually encoded into the first few bits of the IP address as shown in the table on screen. If the first bit was a 0, then it was a Class A network. If not, the router looked at the second bit. If this bit was a 0, then it was a Class B network. And finally, if the third bit was a 0, then it was a Class C network. This scheme came to be known as classful IP addressing, where 192.168.1.0 is an example of a Class C network. The challenge with classful addressing is that most networks were too large for a single Class C network number, which allows only 254 hosts. Instead, many organizations were assigned a Class B network number, which allows over 65,000 hosts, many more than most organizations needed. The end result was that many IP addresses were wasted. These fixed boundaries limited flexibility in the number of addresses that could be assigned. As the Internet grew, the pool of Class B networks grew smaller and smaller. To allow for more addresses, the class scheme was replaced with CIDR, which removes the fixed boundaries and allows for any number of bits to be used for the network portion, regardless of class. At this same time, the Internet routing tables were growing exponentially. To reduce the size of the routing tables, CIDR also provides a way to summarize many classful network numbers into a single routing table entry. This aggregation of networks into a single address is often referred to as a supernet. You can see on screen that a single address range using CIDR notation can represent many different networks. For space reasons, we've shown only a few. In just a few moments, we'll take a look at how you can determine a network number when a network mask does not fall on an octet boundary. But first, let's finish with our example. Our network is shown on screen, now using CIDR notation to indicate the prefix length for each network. What happens when PC 192.168.1.8 wants to send data to 192.168.1.3? First, it puts the destination IP address and source IP address, but not the mask, in the packet. Next, it uses its network mask to determine if the destination IP address is on the same network. If its IP address and the destination IP address have the same network number, which is the case here, it can send the data directly to that address. After the PC determines the destination PC's MAC address using ARP, it encapsulates the packet into a frame and sends the data to the destination. Let's take a look at another example. Here, the same PC wants to send data to 192.168.2.20. Once again, the sending PC applies the configuration network mask to the destination IP address. This time, however, the network number is not the same. Because the PCs are not on the same network, the PC sends the data to the default gateway for further processing. Devices use network masks to determine their network prefix. But a network mask also identifies the valid host numbers on a given network. In any network, the first address, where all host bits are set to 0, identifies the network number. The last address, where all host bits are set to 1, is always reserved as the broadcast address for the network. You might remember that a broadcast address is an IP address that allows information to be sent to all devices on a given network. All numbers except these two reserved numbers are valid host numbers. In the example on screen, 192.168.1.0 is the network number. The broadcast address is 192.168.1.255. Therefore, host addresses in this network can lie in the range that begins with 192.168.1.1 and goes up to 192.168.1.254. If you know the prefix length of a network, you can easily calculate how many individual host addresses are available on the network. The formula to calculate the number of hosts is 2 to the power of the number of host bits minus 2. You subtract 2 because the network number and broadcast address are reserved. In a /24 network, there are 24 network bits. That leaves 8 host bits. Using the formula, we calculate that we have 254 host addresses available for our network. If more host addresses are needed or more network numbers are needed, we'd have to change the size of the network mask, which we'll cover next. Let's quickly recap some of the concepts we've learned with an example. When we last visited the Acme company, they were growing their network, expanding into several buildings on a single campus. Now they've decided to build a new manufacturing facility in a different area of the country. Let's say that you're the network manager at the new location and you're in the process of developing your IP addressing scheme. You have been assigned the address range of 192.168.3.0/24. This CIDR notation, also known as a CIDR block, represents the address range 192.168.3.0 through 192.168.3.255. So, you can use IP addresses for hosts starting at 192.168.3.1 and ending with 192.168.3.254. With the current 24-bit mask, you have one network, 192.168.3.0, with 254 hosts. Now, suppose you determine that you need at least 5 networks or separate broadcast domains, each requiring a unique network number. Each network will have no more than 25 hosts. How are you going to take this single IP address range and break it into smaller networks? The answer? IP subnetting. IP subnetting means taking a single network number and splitting it into smaller networks or subnets, which is short for subnetworks. You create a subnet by changing the mask assigned to each broadcast domain. Said another way, you extend the size of the mask, creating more network numbers with fewer hosts per network. The original address range used the first 24 bits for the network portion of the address, leaving 8 bits for the host portion. To create a subnet, you adjust how many of the 8 bits will be network bits and how many will be host bits. More network bits mean fewer hosts per network. More host bits means more hosts with fewer networks. It's a balancing act. Move the slider on the interactive visual on screen to see how changing the size of the mask impacts the number of networks and the number of hosts possible in each network. Click Continue when you are ready to move on. You might have noticed in this interaction that you could only move the slider within the last octet of the address range. Once you've been assigned a specific network range, you can only make the network prefix length longer, not shorter, because other networks will also be using the first 24 bits. Now let's take a look at how you would actually calculate the number of networks and number of hosts within a network. Let's use our power of 2's table again to help us complete the calculation. First, we'll divide the 8 bits of the last octet in half, allocating 4 bits for network bits and 4 bits for host bits. Using 4 bits for network bits allows for 2 to the 4th, or 16 different networks. That's each binary number between 0000 through 1111. Using 4 bits for the host bits allows for 14 different hosts. Remember that we always subtract 2 from the number of possible hosts because there are 2 reserved addresses. In the scenario we presented at the start of this section, you need at least 5 networks with 25 hosts each. With a network with a prefix length of 28 bits as shown on screen, you wouldn't have enough hosts per network to meet your goal. Is it possible to meet that goal by allocating 3 bits of the last octet for network bits and 5 bits for host bits? Complete the calculations below and fill in the blanks with the number of networks and hosts per network possible. When you are ready, click Submit. Now, let's go back to the question we asked earlier. What happens when a network prefix doesn't fall on an octet boundary? We saw that when a network prefix falls on an octet boundary, it is very easy to determine the network portion and the host portion of the address without looking at the binary equivalent. Here you can see that the first 3 octets represent the network number, and the last octet represents the host address. Remember also that the first number in a subnet is reserved. In this example, it is easy to see that the IP addresses ending in 0 are the reserved subnet numbers, and those ending in numbers other than 0 are hosts. Here are the addresses of the first subnet and first host in that subnet, shown in binary and decimal format. When a single octet comprises both network and host bits, however, it is not so easy to tell the difference between a network number and a host address. You have to look at the binary equivalent. Notice here that with a 27-bit prefix length, the first available subnet number is actually 192.168.3.0, where all bits in the subnet portion are turned off, and the first host address in this subnet is 192.168.3.1. Nothing looks different yet, but let's keep going. The second available subnet is 192.168.3.32, where the far right bit in the subnet portion is turned on. The powers of 2 table on screen shows you how the bits in the last octet now add up to 32. The first host address in this subnet then is 192.168.3.33. Now this address or host address looks very different, and here is where the purpose of the mask really becomes clear. If the network prefix does not fall on an octet boundary, it is impossible to determine the actual subnet number without the mask. Using the subnet mask and converting binary to decimal, we can start to build a table of the network numbers available and the host ranges possible within each network. The table on screen shows the first 2 subnets we just looked at, displaying both the dotted decimal equivalents of the full IP addresses and the last octet of the binary numbers. Now, let's say that PC 192.168.3.60 wants to communicate with 192.168.3.66. Do they need a router to communicate? Once again, the first step is to determine if the two devices are on the same network or, in this case, the same subnet. We apply the subnet mask to the source IP address and determine that the subnet number is 192.168.3.32. Now, if we apply the same subnet mask to the destination IP address, we determine that the subnet number is 192.168.3.64. Because the two devices are not on the same network, they must use a router to communicate. Remember that Acme's manufacturing facility was assigned the network range of 192.168.3.0/24, which they needed to subnet to meet their needs. The table on screen shows each subnet number and the range of assignable host numbers in decimal using a 27-bit subnet mask. The table also shows the last octet in binary of each subnet, as well as its corresponding host address range. Remember that there are two reserved addresses in each subnet. Now let's assign a few of these subnets and see what the new IP addressing scheme looks like at the Acme manufacturing facility. In the graphic on screen, you'll see that we've assigned three subnets: 192.168.3.0, 192.168.3.32, and 192.168.3.64 to the three different networks. We've also assigned three host numbers from each subnet to the network devices within each subnet. Notice that the router has three network interfaces in three different subnets, so it must have a unique IP address for each. Now you try it. In this exercise, let's say you've been assigned an address range of 192.168.10.0/24, but you want to subnet your network to meet your business need. Your goal is to create 4 different networks with at least 50 hosts per network. First, decide what prefix length should be used for your networks. How many bits of the last octet should you use for the subnet portion of the address and for the host portion? Move the slider to indicate your answer. Then, click Check Answer. If you'd like a hint, click the Hint link. Not quite. Try again.